Hey, thanks for watching. This video is from the second annual HVACR training symposium that we did down here in Claremont, Florida. This session is from Rick Sims, and the title is Conductsation, which when some people saw it, they thought it was a typo. No, it's not a typo. It's just that the session is about condensation on ducts, and Rick is a clever fellow. Hands down, this session was the session that I heard the most feedback that it was really transformative in the way that people thought about the problem of condensation. He went into great depth about the water molecule and how it functions and how we can prevent it from building up on surfaces that we don't want it to. So big thanks to Rick Sims for doing this presentation, and thank you to all of our sponsors and speakers who made the second annual HVACR symposium possible.
Welcome. My name is Rick Sims, and for the next course, I'll be going through a course we call Conductsation. It started in 2016. It was developed in Climate Zone 1, which is the most humid climate in the 48 states. And it grew out of a discussion about sweating air handlers, and particularly the way that tech support from the various manufacturers of air handlers were dealing with their equipment sweating. So the name of that was Cold Air is Not a Malfunction. And we grew from that into this. This course is all about the dew point versus the surface temperature. And so we're going to have all kinds of strategies that we're going to evaluate that have to do with controlling the surface temperature, because there's so little that we could do. We have one strategy to control the dew point. What's the strategy to control the dew point? Don't put it outside. Don't put it in unconditioned space. So, if we could do that, if we could put all the ducts in conditioned space at a low dew point, then that would solve it. Well, this is for all those times that for whatever reason you have no choice. You have to put the ducts in a vented attic, in a cool, wet parking garage, wherever it happens, a crawl space, wherever you have to do it. So the only thing we can do here, since this is all about dew point, and we can't control the dew point, versus the surface temperature, this is all going to be strategies of how you can limit how cool the surface temperature gets. You will not have to do a lot with this little chart that Mr. Carrier made. About all we're going to do this morning is about the equivalent of looking at a map of North America and saying that's Texas and that's Florida. That's all we need you to do this morning. So for example, I've plotted the design conditions that I use in Naples, Florida. The ASHRAE design condition gives us a 72-degree dew point. Now, you don't have to do any math with this chart, and we're not going to go into it that far, but everybody here does understand that the shape of this chart is because air holds more moisture when it gets warmer. And so the chart is fat on one side where it's warmer, and it can hold more. But additionally, since we're going to use the term dry bulb and dew point, I want you to make sure that you understand one other thing about it. This chart, of course, has hotter is this way, warm air holds more heat, and moisture, grains, is this way. How much moisture can the air hold? The dew point is the point where you've hit 100%, and so you have this condensation occurring. The thing I need to make sure everybody understands is that we're at 50% outside, and we're at 50% inside. And you have to understand that concept that if you're not in the habit, I'm assuming a lot of you are service technicians, if you're not in the habit of writing down the temperature that goes with a relative humidity measurement that you've taken, get in that habit, because relative humidity doesn't mean a thing to us when you tell me it's 50%. And customers do it to you. I got 50%. Is that okay? You know? Or the service tech writes down 50%. These are both at 50%. They're both at 50%. It's just that 95-degree air can hold a lot more moisture, and so 50% would be 120 grains. I love the math for climate zone 1. Look at the grains. It's exactly double. It's exactly twice as much moisture per pound of air. So how do we use this? Well, I'm going to take and look at the how it affects us. It primarily affects us during rainy season, and at the beginning of rainy season, we see it start to happen on the cold parts of the ducts, and then toward the end of rainy season, you are more likely to see saturated ducts because it builds up over the course of the season over time. One of the things that's extremely predictable is that the climate zone 1 dew point, at least at the Naples Municipal Airport over the last 15 years, has been an average of 73 degrees. Now, the reason that's important is because that tells you where the duct has to be, or the air handler cabinet. In other words, in our climate in Naples, Florida, if you're going to have an air handler cabinet that's cooler than 73 degrees, expect it to get wet. And that would not be a malfunction. That would just be normal. Same thing with the duct. If the duct can reach 73 degrees, then you're very likely that you're going to get some condensation, so it should be anticipated. Now, the daily spikes that we record, usually in the early morning hours, we can have an 80-degree dew point. And as a matter of fact, we can have a higher dew point inside an unconditioned space that's filled with fluffy stuff. That pink stuff. How many of you have a psychrometer that has 2 heads on it? Field piece makes one. You like that? Isn't that nice? It's got 2 heads on it, so you always know if one's lying, right? Because they got to read the same thing. Next summer, when you're in one of these cases where the ducts are sweating and you look and you see this pink, fluffy, blown-in insulation, Andy Oss turned me on to this. Stick one psychrometer tip down in the fluff, put the other one up in the air. It'll blow your mind how wet that insulation is. So you don't just have one dew point, which was the way I started training. I put it this way the other night. When I started training, Hotel California was the #1 song. So that's, you know. So anyway, we kind of were trained that you got an indoor dew point and an outdoor dew point. With building science in the last 20 years, one of the things we've learned is the molecules tend to be on the stuff. And so we'll be looking at how that works. Now, this is the time of year when we get these fronts from up north, when the polar vortex pushes down some nice dry weather from outdoors. And if you have sweating duct and sweating air handler problems for this part of the year, you will probably find something that's wrong. What we find is that for systems that are set up well commissioned, they're running reasonable static pressures, they're running the anticipated flow rates. What we see with those is that they work pretty good until you get into that rainy season. It's more likely your air handler is going to sweat in climate zone 1. This pointer doesn't work, but if I could point, I would point to this Naples, Florida. That's where we're at. Climate zone 1 is basically Naples to Miami. So the difference is not that you don't get humid. Steve Rogers from the Energy Conservatory, he sent me a photo of his phone showing an 80-degree dew point in Minnesota. So it happens. It's just that it doesn't happen for 4 months. That's the difference. Let's see what else is on here. So let's start with materials. We're going to take a look at some of these materials and how they're going to work. And the first one that I'm interested in has probably the most published about it when it comes to this. This is familiar to you, right? Fiberglass ductboard. You can find all of the information that you want about this stuff, an incredible amount of stuff, for free from the National Association of Insulation Manufacturers of America. And all kinds of stuff you can download. And some of the stuff that's on there is specifically about what to anticipate with regard to, is the duct going to sweat? Well, the bottom line is the people that sold you this, that made it, they told you it was going to sweat. So you can't be surprised that it's sweating because they said it would. And here's where they told us, if you put that stuff in a place where the relative humidity is 90% for any reason at all, it's going to sweat. And it doesn't matter if you use R8, R6, R4, it's not going to matter. Because as you can see, they're telling you, we don't do 90%. So if you put me in a place where, now the other thing you see, this is the area that you'll see as we go through this where the biggest problem occurs. I've got it shaded blue here. And right here where this green line, this is where we lose control of R8. And this is where we start to condensate with R6. And so you can see that there's quite a bit of exposure there, quite a bit. So what if we just insulate our way out of it? Why don't, if we make it thick enough, right, should work. That's one strategy. You can do that. If you want to solve this problem completely with insulation, anybody know who that guy is? Joe Steebrook, pretty smart guy, moisture and things. Joe is showing us these foamed ducts. Here's a picture that Paul Mass from Building Science in Tampa took of them foaming in some flex duct. They're just using this polystyrene foam board as a form, and then they'll pull it off when they drywall. But what they're doing is they're encapsulating this duct to a minimum of R13. Paul and I were discussing this photo. We don't think they did it right. The reason we don't like it is because they've got the flex duct laying right on the wood, and they've basically created a composite, and the wood is part of that thermal composite. So the wood is going to get damp and turn black inside of the foam. So if you wanted to do this, don't do it like most people do it. As a matter of fact, I never liked this because I never saw one that was done nice. And then I saw Jason Julian in Alabama, and that changed everything. This is Jason Julian Heating and Air Conditioning in Alabama is coating their sheet metal pipes, hanging them beautifully. And that I like. The reason I haven't liked R13 non-permeable foam ducts is I haven't seen one done this nicely. What I've just seen is just somebody just went in there and just, just made a big lump of foam. So I really like what they're doing up there in Alabama, and I gotta say in Florida, I work on sometimes $50 million homes, but I haven't seen this yet. I haven't seen anybody do this nice, the way he's doing this. This is a basic formula for determining how cold is the duct going to be. Because we already said, well, if we're going to be in climate zone 1 and the duct gets cooler than 73, it's going to get wet in the summertime. So we could use this formula, but I will point out that this is a very simple formula that does not include any radiant heat. In other words, this is just conduction. And so this would be the temperature of the duct maybe on, if it was in an attic with some heat coming down, it would be on the bottom. Okay, so generally it'll be, if anything, it'll be warmer than this. But what I'm going to do here is take these temperatures and we're going to look at it under a couple of different circumstances where the air around the duct is 75 degrees, the air around the duct is 80 degrees, or the air around the duct is 90. Then we're going to throw some variables at it, like is the supply air temperature 50? Is it 55? Is it 60? And we're going to just take a look and see, well, what does that do to us? So the first comparison that you want to make is this one. Actually, this is the second point of this today. The first point was you can insulate your way out of it, but what does it have to be? R13, and what else? Non-permeable. It can't be permeable foam. So that if you can pour water through the foam, that's not the right kind of foam. It's closed cell foam is what it needs to be, and it needs to be R14. You do that, you got it. This is a comparison now of what happens when you raise the temperature or decrease the TD. Now the reason this one's important, in my opinion, sweating ducts is very, very seldom a service call. What is this guy in this truck going to do about it? He's got one move in his playbook. What's a service tech going to do? Well, it's vented. It's vented. I mean, you know, we have to, you know, dehumidify the outdoors. But I'm with you. But see, now you're cheating because now you're putting it into conditioned space. And, you know, that, you know, if you had that luxury, why wouldn't you? Why wouldn't you put the duct in conditioned space? But if you don't have that ability to do it, and we'll say, well, we have to put the duct outside for whatever reason, then my point is that if I'm a service technician and I'm expected to do something about this sweating air handler and these sweating ducts, well, you know, you can take the static pressure and check and see is it restricted? Is there a dirty filter? You can look at all, it's moving air. It's just sweating like a pig. Well, the only thing he can do is raise the fan speed, right? Doing it for years. It's sweating. I guess we'll raise the fan speed. Even though we really wanted to design it with a low fan speed, and that was the best scenario for what we were doing, we end up selecting a fan speed just so we don't rain on the duct. So it's a heck of a compromise, but it's the only thing that a service tech can do. What's a service tech going to do? Pull all the duct out on a service call? So he hasn't got a lot of choices. Most of these problems have to be solved before the duct is installed. Here's what happens. A 5 degree, we'll look at R6. A 5 degree increase in the supply air duct. We were running air leaving the coil at 50 degrees, but the cabinet's sweating. So I'm gonna speed up the air handler, and when I do, the air handler is now 55. We raised it 5 degrees. You get about a 1 degree increase in your duct temperature from a 5 degree rise. So that's your second question answered. How much will I raise the temperature of the ductwork so that it won't sweat? Can I get it above the dew point? Is what you're trying to do. I'm trying to warm this duct up. Well, if I speed up the air, what if I speed it up so that I got a 60 degree leaving air? Now, that's not great for many reasons, but I got 60 degree leaving air. I only gained 2 degrees. The duct's only 2 degrees warmer. So you have to change the supply air temperature by 5 degrees to get a 2 degree, or no, by 10 degrees to get a 2 degree difference. You got to change it by 5 degrees just to get 1 degree. So that's all that poor service technician can do. Now what's he going to do? Right? He's there on a service call. So he doesn't get to do some of the other things that we'll talk about because it's just not in the scope of a service call. And look what's happening here. 90 degrees. Look at these dew points. These are the surface temperatures of the duct. It's in the 80s. That's pretty safe even in climate zone 1. So as a general rule, I say that if the air around the duct is 90 degrees or more, it shouldn't be sweating, because the dew point would have to be in the 80s. So that's why we expect most of the condensation that we experience with these things to occur at 80 to 75 degrees. And when does that happen during rainy season in Florida? Every night. Every night. It's 95 in the daytime. Is it 95 at night? No, it's 75 to 80. And that's when your ducts are getting wet, while you sleep. While you're there on the service call, they're actually drying. So you can actually go to the customer and say, I checked it out, they're drying right now. You know? See if it works for you. It didn't work for me, but try it. Okay, so the next question is, what if I use R6 instead of R8? One of the things that we've proven to ourselves in our climate zone for years is there is no energy payback for R8 ductwork. And it's been, I'm on one of the building code committees where our values are over-discussed, in my opinion. But anyway, the R8 duct board, if you've ever used it, add 4 inches to your duct dimension. So if it's a 10 by 10 duct, it's going to be 18 by 18. Or excuse me, it's going to be 10-inch duct is going to be plus 14 by 14. The change from R6 to R8, we'll look at it at 90 degrees. At 90 degrees is where you get the most bang out of it, but you still get less than 2 degrees warmer. So it really doesn't do much, 2 degrees. And really where we need it, which is down here at 75, which is nighttime when it's cold out, we're only getting 1 degree warmer. So by going from R6 to R8, and that's exactly what NEMA tells you. So it's not like the people selling the duct board and the insulation are saying that it's going to be better than that. They're not. They're telling you that, yeah, you get a little better. So you don't get a lot of bang out of that. Here's the big one. This one's huge. With only a 5-degree increase in your temperature of your air. So let's say you're thinking about, in your mind, you're thinking about ducts in an attic. If the attic temperature goes from 75 to 80, it increases the duct temperature by 4 degrees. So that's usable. And the other thing is, by the way, it can go the other way. For example, the home was shaded by a tree, and then Irma came through, the hurricane, takes the tree out, and now the temperature is warmer. So they changed the color of the roof. They put a cool roof on it. Now they can make shingles that are colored shingles that reflect heat. We used to always think about white. They now have technology where colored shingles are reflecting heat, but it's not a white or reflective color. But this is the big one, because if you go from 80 degrees to 90 degrees, if it gets warmer by 10 degrees, that's an 8-degree rise in your surface temperature of your duct. So here's the summary, and this is what you get when you actually spread it out and look at it. A 5-degree increase in your outside air temperature raises the surface temperature of the ducts 4 degrees, and it is the biggest factor. So for example, that explains why a parking garage is so hard to deal with. You got any radiant heat in a cold parking garage where you got lots of air going through the parking garage because it's got these big fans for the car exhaust, but it's underneath a cold slab. That's a duct that wants to sweat, Whereas look how much difference it makes with a little bit of heat. So a 5-degree increase in the outside, the air around the duct, will raise the surface temperature of the duct by 4 degrees. Going from an R6 R value to an R8 will get you less than 2 degrees, but where you really need it, which is down in the 75-degree range, you only get 1. So it doesn't help that much. And then the one that everybody does because it's cheap, it's easy, whether it works or not, for every 5 degrees that you decrease your TD is basically what you're doing. Hopefully you're manipulating fan speeds and not refrigerant charge or something goofy. But if you're just changing the fan speeds and you can get a 5-degree rise, that'll get you 1 degree. But it has a lot to do with how it's installed. Now, you remember that I said that ducts don't sweat when it's over 90. So here's we got a 73 degree right on the edge of wetness, 73 degrees, 55 degree air on the inside. We got an 18 degree temperature difference across the wall of the duct. Everything's going good, and then we do that. And that is going to be a problem. As soon as we put this up against this, it's going to get wet. It needs a gap. And what's going to happen is in between this, you've made a composite. You're conducting, you're touching. You're conducting right through. You've made a 67 degree area on your duct that would have been 73. But because you put it up against a piece of wood, you've composited that wood right into your ductwork. The only way you could make it worse, and you've seen this, is let's paint mastic over them and make them all one. We'll just mastic the whole thing so it's one big clump. And this is really a very common problem. And here's what you want to remember about that. Just a ½ inch of space is 1 R value. Now you remember how you had to drop your TD by 5 degrees just to get 1 degree. And if you spent the money and the labor to go from R6 to R8, which is substantial, you would only get 1 degree. You can get 1 degree just by not touching this. The R value of a ½ inch space between the duct and the building component is almost 1. And when you get into 1½ inches, it's R 1.08, so it's just figure it's about 1. And you notice that the main thing is that it doesn't touch. You don't get a lot of bang to go from 1.5 inches of space to 3½ inches of space. It doesn't do that much. You get a big bang just because it doesn't touch. So let's say a ½ inch. Let's say there's a ½ inch, because at least we know we get, our duct is going to be 73 degrees, not 67.
We're in North Carolina, but we've had some houses with flex duct in the attics, like where it was put in a new construction and was laying basically on the sheetrock. Then they came in and blew a lot of insulation on top of it. And we've had some cases that we go over there and it's getting water spots on the ceiling, and like you said, that insulation is wet.
In what
down
state?
North Carolina.
North Carolina?
Yeah.
Yeah, I can see that. That's exactly what we're talking about. As a matter of fact, I have a slide of that, of exactly what you're talking. And what he's talking about is ducts just laying on the ceiling. It's not even that uncommon.
You ever check the temperature between the sheetrock and the insulation and above the insulation in the attic? It's hotter when you get to the sheetrock than it is on top. And you're compressing your insulation on your flex, so you're losing your R value.
Did any of you get to see excellent speaker last year, Allison Bales? Allison Bales is phenomenal building scientist, PhD, certainly better speaker than myself. He is in a world somewhere beyond climate zone 1 where they can bury ducts and they don't sweat. And I've had a few beers with him, and I've just told him it's just we can't do it. And I get it, you know, because he's trying to insulate by putting it under the fluffy stuff. And the other thing I can tell you is that's fine with us for an air return, right? An air return is going to be above the dew point. It's going to be at 75 degrees. Now, if the customer is running at 70, maybe it'll be a little more, but should have a duct gain, right? If it's in this situation where we'd even be talking about it, it must have a duct gain. All right, well, let's keep going here. And so here's our situation. And who warned us about this years ago? No audio? It's hammer time, man. Hammer time. Guess no MC Hammer for you, sorry. MC Hammer, the 5-time nominated, Grammy-nominated artist, was also a visionary in building science. And the building science community has never recognized, but he warned us. He told us. What did he say? And is there really that much more to it? I mean, he begged us, but... So how do you... whoa, I just lost everything? How's that go? There we go. Yes, sir. Return air duct would probably be okay buried. Return air duct would probably be all right, but the problem with burying 50 to 55 degree air in 80 degree dew point fluffy stuff, unless it has R14 non-permeable, which then we don't care what you do, right? Then don't do it. So my recommendation is climate zone 2 as well. I'm going to say don't do buried ducts. I don't recommend it in Florida. Yeah, as a matter of fact, I'm going to say don't touch this. That's what I'm going to say, because what I measure is that the dew point in the attic might be 75 degree dew point, but I stick that psychrometer down in this fluffy stuff, and we're going to talk about why that is. You know, moisture molecules, they love surfaces. They don't want to be in the air. You guys see Mr. Bergman's thing about this morning about desorption? We're going to get into that because it's the same thing. It's just what he's talking about is happening inside copper tubing. And what we're doing, it's the same thing, but it's on the outside of a duct. So actually, you got to help me out. Explain MC Hammer to the millennials. Just handle that. Explain it to them. It was actually, that was my daughter for me. You know, my daughter would have bought that, you know, not me. So, wrong time period. Now, this is one of the most commonly misdiagnosed things. It's so simple in the business. It can be just a horrifying thing for a Port Royal princess or the realtor or the interior desecrator. You know, they look up at the grill and there's black stuff on the drywall. Oh my God, you know, we've got to do something here. Well, one of the lazy things that we do sometimes is just, oh, that's a duct leak. That's a duct leak. Wet around the grill, that's a duct leak. Well, let's send the skinniest, smallest guy up there, and he can create some thermal bridging. Now remember how we're not supposed to touch things. Well, not only are we touching things, we're thermal bridging to all this. Just piling mastic creates thermal bridging. You don't get extra points for mastic. Mastic, let's see here. I got a square foot of everything today. I got a square foot of mastic. Here it is. Is this an insulation? No. This is a sealer. And you can't code it up like Bondo and get an R value of it. It's not intended to be used that way. So compounding, what I mean by compositing, piling this stuff up and compositing this to this is not a good plan. Where we're just going to, oh, we'll just paint the whole thing. We'll just paint it all in together. If you want it to be dry, then that's not a good plan. Now, if you don't want the air to leak, that might be okay. But one of the reasons that this is often misdiagnosed is because it doesn't solve one of the most common problems. Any of you guys put in linear diffusers? Do you ever look at them in thermal? They leak like crazy because they don't have any gaskets. And the diffusers that do have gaskets often have crappy gaskets at no extra cost. And so what happens is this is very frequently misdiagnosed. This is not a duct leak to unconditioned space above the drywall. With thermal imaging, look a little longer. It's not just that it's damp. How is it damp? You can see with thermal imaging when the air is blowing out from under a diffuser. You can see it on linear grills. And you can even point it out. Now, if you just look and say, well, it's wet, if it's damp because it's cold and leaking behind it, it'll look more like watercolor. You know, it'll be more rounded and faded into it. It won't look the same. When it has pointed, feathered edges, this is clearly the air going between the flange and the drywall, and we got 120 grains of moisture up above that drywall, so it's going to get wet. So what do you got to do? You have to stop movement. All you've got to do is stop the movement. So one of my favorite products that we're going to be all over today is this stuff. Love this stuff. It's like coolie cup for anything. It's adhesive, closed cell foam tape. So it's most often service technicians use this stuff to put on a thermostatic bulb. That might be a good use. This is like pipe insulation with an adhesive on it. All right, so that is one of the ways we can solve that. And let's just keep moving here. There's only 20 degrees difference between this ceiling and the duct. So we go down below and we look at it in thermal, and we can see damp, cold spots on the ceiling where the flex is laying. Well, it's easy to fix. That's the problem. Does that look a lot like the stuff that was laying on the ceiling? Yeah, usually. The usual suspect is usually involves some sort of a triangle with some sort of a worm coming out of it. And that's usually black when you pull that out, you know. Hang it above. So what do you do with this?
You can't touch this.
Give it a little space here. And what did we say? If you gave it a ½ inch, you'd get an R value. But I'm saying do better than that. You know, pull it on up. Get it off that cold ceiling. If you don't want the surface of this duct to be cold, then get it up off that ceiling. And what we want you to do is have a 40-degree temperature difference between the inside of the duct and the outside of the duct instead of a 0. When you put it on, or 20, we'll do 0 here in a minute. There we go, there's 0. What,
You can't touch this.
what if I put a 55-degree duct and lay it on top of a 55-degree duct? What's the temperature difference? Why would this be anything other than 55? I mean, it's trying to get there, right? I mean, we're doing everything we can to make sure that the bottom of this duct and the top of this duct is going to be cold. It was installed to be cold. So that's why MC Hammer is upset. So that's how you fix it. High-tech stuff, right? You lift it up, you give it a temperature difference, and things change. You'll also, people who have some experience tearing things out and throwing them in dumpsters have seen black marks, right? See the black marks on the wood where the old ductwork went? You can see where duct was because it leaves a black mark where it was damp, wherever it was touching. It's better to use a, uh, a galvanized hanger that does not have a lot of thermal mass would be better than using wood. Also, it's non-permeable, and mold doesn't really eat metal, but mold kind of likes wood. So I would, this is not out of any manual, and this is an opinion. My opinion is that's a superior hanger to a 2x4. And to tell you the truth, I don't think it costs any more than a 2x4 these days. Metal strap doesn't, but a metal strap's a pretty good way to hang a duct. How about that? Full circle back to 1950, and still the best way to do it is put it on a metal strap. Thank you, MC Hammer. Turbulence is also a problem because this is about that mass flow rate. We were talking about mass flow rate this morning with regard to removing molecules with a vacuum pump. Now we're talking about trying to put those pounds of air down the middle of the duct. And we know from, any of you guys do duct traverse ducts, okay? Most of the air is moving down the middle, right? That's why we measure it that way. And so we take more readings away from that. I believe generally if you take a velocity pressure reading in the center of a straight duct, that's, and multiply times 0.9, that's pretty close to what it's going to be. So most of the air wants to go down the middle until we start putting offsets and turning it. And, you know, the internet is full of pictures of bad ductwork. We could make the class that. But you get it, run it straight, pull the kinks out of it, shorten it, hang it. And these are the common sense things that will help. Flex collars, obviously, if they leak underneath the liner, then the liner will get cold. But the other way that's a problem is if you create thermal bridging. A metal collar is colder than the flex duct, and the metal collar is on the inside. See, the air barrier is switching from the outside to the inside. So on the trunk line, the air barrier is on the outside. But on the flex duct, it's on the inside. The tap collar is where it goes from the outside to the inside. And so what we don't want to pinch the insulation. We want it fluffed out around the collar. We don't want mastic piled up like I show it right here, because mastic is not insulation. That mastic will just turn black and get damp. We want it like that. We want just enough of an air barrier to carry the air barrier from the inside to the outside, and then we want enough insulation to keep that whole collar underneath. In Florida, you have to tape the outside liner. I know in some states you don't have to do that, but in Florida's building code, you do have to, even if you seal the inside, you can't just fold the outside around and panduit it. You can't do that in Florida. You have to seal it. What about ducts that are in the conditioned space? That's one way to do it. If you don't want to foam and create a dry, low dew point space up above your ceiling, then one of the things that's done is, well, I'm going to have a vented assembly above the ceiling, but I'm just going to put all the ductwork below it. Good plan. Excellent plan. In other words, I got a vented attic, I just don't put ducts in it, and I certainly don't put an air handler in it. That's a good plan. That's not a bad way to build a building. But if you do that, do give yourself a little bit of space, because when you put this ductwork up against the drywall, remember you've got a 55-degree air temperature, and you're chilling this drywall down in the dampest part of the house. So all you got to do is don't touch this. Half inch will do it. Just give us a half inch, but don't touch. Don't put the duct all the way up against it, or it's going to get wet. This is business as usual. We have some radiant heat, and then we've got this crappy spaghetti duct just splattered all over the home here. And the cool knee wall is a place where you can see all kinds of things happening because you don't have your typical radiant heat source because you're right up against this cold knee wall. So everything's different. Usually looks something like this. Here's the cold knee wall. Here's the duct laying on the cold plywood, and the air handler and everything's dripping. If you're going to have a vented space and put a piece of equipment in it, you might want to select an area that has more radiant heat. This is the building cavities that we can't do anything about sweat in those. If you run ducts through those and then you start moving air through those cool cavities, we can't help you. We can't, there's nothing we can do. The builder or the retrofitter, somebody's got to give us an air barrier. We need the inside of this house to not try to be the same thing as the outside of the house. There has to be a break somewhere. Now, the harder thing to be successful at is sealing in the ends of these floor joists. What you're looking at here is the ends of the joists that are running through the floor joist. So in that case, you've got 120 grain moist climate zone 1 air around your duct, but you've only got 70-degree rooms around it. So you've got all the moisture, but you don't have any heat because it's sheltered by the room above. So if you move it up on top, it gets a little more heat. But then we usually, if we're going to do things dumb like we're doing here, we usually put in the big, goofy roof cap. That is also the best method for the rats to go in and out unimpeded. It's their favorite entrance and exit. They are not installed, they're very seldom installed right. The correct location for an attic vent, if you're going to vent an attic, where is it? The top. And putting the thing halfway down usually results in a lot of infiltration. If you want to do it right, here's how you do it. You want 300 square foot of opening for every 100 square foot of floor area. And then we want you to put 40% of it at the top, and we want you to put 60% of it at the bottom. So that is much less than most people have. Now, if you ask the best builders that money can buy, how did you calculate the area of the attic vents? It's 4 inches and it goes all the way around. They have no idea. Nobody ever calculates it. So Joe Steebrook's been telling you for 20 years that it's supposed to be 300 total for every 100 square foot, and you're supposed to put 40% of the opening at the top and 60% at the bottom. In other words, basically what he's doing is he's giving it just enough ventilation that convection could work if everything else is right, but he's not allowing wind and cross-flow ventilation to just be moving molecules of moisture through that space. He's not going to allow it. You can do the big crappy spaghetti duct, lay it all on the ceiling, do whatever you want to do when you foam it. You'll get away with it. As a matter of fact, I have never seen a encapsulated space, unless it had leaks in it, with sweaty ducts. You can get away with really, really bad ductwork, which is a good thing because crappy ductwork is extremely popular. It's everywhere. We can't keep it on the shelf. It's everywhere. Now, the problem with the crappy duct is we have no idea where it came from. Because I know contractors, and I've asked them, do you put in crappy duct? No, we put in the best. I have asked, so it's a mystery. Nobody knows where the crappy duct systems came from. One theory is spontaneous fabrication. All right, let's talk about the exposure moving these molecules. Still air is pretty harmless stuff, so here we got an example. We got still air in the attic space at 12.7 gallons. We've got still air in the interior part of the house at 18 gallons. Is 18 gallons of moisture in the air, is that uncomfortable? Well, only if you're uncomfortable at 75 at 50, because that's what it is. So yes, there's moisture in the air, but my point is it doesn't condense until it moves. So here's what it does. Moving air adds 110 CFM, or each 110 CFM adds 1 gallon per hour of moisture exposure. So that's 24 gallons a day, 168 gallons per week, 672 gallons per month for every 110 CFM. So that's why, if you want to have some fun with this, use data loggers. Do you use them for building science? Because what you do is you put your data logger in the attic space and you set it for a couple of days. You let it run just the way the attic is, because every day in the summer is about the same conditions. You're going to measure about the same thing. So measure 24 hours of it, and then go back and leave the data logger alone, but seal off the big, goofy roof caps. Just put pieces of fiberglass in them to stop all that wind, that cross ventilation, to stop all those molecules of moisture that are going across your duct. Seal it off. Then you go to TruTech Tools and you do what I did. I bought $700 worth of duct mask. And somebody was saying, well, man, you must be doing a lot of duct testing. No, I'm sealing up the eaves. So I go through a lot of dust mask. You know, you guys know what I mean by duct mask? It's the stuff you put on when you do a blower door test. You mask off the diffusers. Well, you can mask off the soffit outside the house with a data logger up there and seal the stupid roof caps, and you can watch it get drier without doing anything else, and you've recorded it. As a matter of fact, you're anticipating what's going to happen when they foam it. That's how this started. Well, Rick, you say I should foam this attic. Well, what's it going to be like? Do you want to see? Well, if I seal off and I don't let any moisture through the big goofy roof cap and I don't let any of it come through it makes a world of difference. And you can, in Florida, I don't know about other states, but in Florida, you can seal your attic by any means you want and put a dehumidifier in it and keep the insulation on the ceiling. That's totally legit, and it works. So just like you put a crawl space, if you want to put a dehumidifier in a crawl space up north, I'm assuming you seal the crawl space, right? Yeah, you're not gonna put a dehumidifier in it unless it's sealed. Well, it'd be the same thing with an attic. If you don't want to do the foam, but you want it dry, you can just seal it, because the whole point is keep the moisture out. That's all you got to do. How do you keep the moisture out? Well, you seal the holes in the boat. That's what you do. Okay, let's go to the next one here. All right, so everything that we just went over is more or less about conducting heat. So it's all conduction. We're going to look at radiant, because radiant can solve all kinds of things when it comes to duct sweating. You can get away with a lot of stuff with a hot enough roof deck, because there's so much heat coming off that roof deck. You felt it. If you've ever worked in an attic, you felt it. That's enough heat to keep you above the dew point. So this is the heat behavior. Yeah, that's good. That's it. Thank you. We're going to look at how heat behaves in this simple shape and things that affect it. When you troubleshoot this, one of the things that's different about it is this thing gains heat in the daytime, but it gives off heat at night. And that's not like we're used to. Generally in the summertime, down in the house, you know, the air-conditioned part of the building, you have a heat load, heat gain at night. It's less, but you have it. But think about it, your attic doesn't. Your attic is giving off heat, just like why does your car windshield, when you get up in the morning and it's covered with dew, why is it covered with dew? Because it was emitting heat to the vacuum of the sky. It was going from hotter to colder right into space. So that is also occurring in an attic, and don't forget it, because a lot of times, well, almost all the time, you're not there at night. When it's really getting wet, you're not seeing it. So if you're taking measurements, chances are that while you're there, you're measuring, you're saying, man, that shouldn't be wet. Well, the reason is it's drying. It's just not dry yet. It got wet last night when the attic got down to 80. Well, then you get there and you take out the access and it's 80 degrees. No, it shouldn't sweat. It was already wet. And then in some cases, you have thousands of pounds of lumber, which gives us thermal storage. So we can soak up a lot of heat during the daytime, and then that heat battery, that energy, keeps it warm. Now, if you have a drop ceiling in a building like this, you don't have that. You don't have all that lumber to store all that solar energy to keep things warm on into the night. In a steel building, there's not any thermal storage at all. The temperature changes rapidly. So we're going to look at how the heat changes things when we change the reflective roof. One of the ways to make ducts sweat is simply reflect the heat. Don't allow the heat to come into the space to begin with, and you'll have a cooler attic, which is more likely to have the sweaty ducts. Less transmitted. The same thing will occur if you use radiant barrier. Radiant barrier film is installed on the inside. It's the shiny stuff. Just expect the ducts to sweat in Florida if you choose that. If you choose to put in a radiant barrier in Florida, I'm going to say all the way up to Jacksonville, really, I don't know why you wouldn't expect the ducts to sweat. I'm going to predict they're going to sweat, because you're not going to have those you're not going to get that radiant heat that kept it from sweating, because the radiant barrier film's not going to let it through. So we're exchanging heat not only through the roof, but the lack of heat between the ceiling and the duct. Obviously, it's going to be a lot cooler down by the ceiling, down by knee walls, and the higher we get up in that space, the less it's going to be. You only have radiation, conduction, convection, so whatever diagnosis you go out and you give this, it has to fit within that, because we don't get to make stuff up. It's either going to be radiation, conduction, or convection. You can write fusion if you think you can sell that, but probably you'll just get away with those three. Another thing to think about, right there we've got a return air duct on top of a cold cabinet. We're looking at normal venting here. The correct venting is 1 square foot per 300 square foot of floor area, and we want 60% of the area of that soffit to be at the bottom. We want 40% at the top. That path of moisture and outside air that's venting that roof, does it have any reason to come near the air handler? Not really. It's got a path set up, and it's limited, it's controlled. But that's not what we really build. What do we really build? Big, goofy roof caps. And the big, goofy roof caps are a way to convey hundreds of CFM of airborne moisture and cross ventilation through the attic. So some people say, well, doesn't it make the attic cooler? If you want to make the attic cooler, anticipate the ducts are going to sweat. That's where we started, right? What was the biggest difference? The biggest difference was the temperature of the air around the duct, remember? That makes a big deal. It only makes a little deal what the air is on the inside of the duct. So this is a bad situation. So what I recommend you do when you find this, how many times is the air handler like right next to that thing? Right? The air handler's right, and there's the big goofy blowing cold air on this cold cabinet. Why wouldn't this sweat? So anyway, put your data logger in that space, take some duct board, seal these off, Go buy some dust masks, seal these off, and watch it stop sweating. Simply because you took the moisture away. You dammed it up. You're not letting the moisture get to the duct. All right, so we're going to look at what happens when you lay a duct on top of an air handler cabinet. This is a very common reasons that ducts would sweat. If you lay a duct on top of an air handler cabinet, you're shading it. There's no radiant heat. The worst thing you can do is let it actually touch, but it would be better if you just didn't have any duct on top of it at all. And the other thing that's true is if you put the supply air duct on the top, I'm going to go back a minute. If you put the supply air duct on the top, which is the one you're worried about sweating, you can't obstruct the heat from the roof. If you put the return air duct over the top of the supply air duct, it can shade the radiant heat. So now or if you put any duct across the top of the air handler, you're shading the air handler. So radiant heat works just like shade. So there's a lot of merit for hanging ducts very high, hanging air handlers on threaded rod, trapeze hangers, getting them up off the cold deck, and putting the warmer duct. Now, the other thing about this, does a duct gain by heating up the supply air duct? Does that hurt the performance and comfort? No. That's reheat, baby. That's reheat. Duct gain is great. What about return air duct gain? Ooh. Now we have a penalty. Because when you warm up the air going into an evaporator, things don't go the same way. So if we're going to get a duct hot, we always want it to be the supply. You know, we don't want it to be the return. So this is the one that we'd say, okay, go ahead and bury this one. We'll let you bury that one in the fluffy stuff. We're not worried about it. Let's keep our coldest duct up on top and hung high for the best chance of success. This is the worst spot in the McMansions down in Naples. There's lots of these knee walls, and the knee walls block the radiant heat. You don't have radiant heat coming from multiple directions the way you do when it's just a big open attic. And so you end up with very cold spaces, and usually they got the big goofy roof cap. They got it right there, right next to the air handler, just to make you angry. And look what else happens. What happens to convection on a cold wall in an attic? It's going down. That's a cold wall. It's not going up. It's going up the other wall. It's going down this one. So be aware that convection, you know, it's disrupted by this. So this theory about how we're going to vent the attic, it only works if everything goes up by convection. So just remember, when you have a knee wall, you've disrupted the convection. So pull the air handler away from it, and the air handler and the duct will both be warmer. So what you don't want to do, now here's something. The service technician we talked about, all he's got is, well, I'll speed up the fan. That's all he's got, right? What else is he going to do? Somebody at your company has the authority to say where the air handler goes. So if you don't want the ducts to sweat, get that person to keep these things in mind. That if you have a choice, could we please not put the air handler right up against the cold knee wall? Service tech, it's too late. Whatever they did, you know, and he's got to make a call out of this. In my opinion, if you really want to solve the customer's problem and they have sweaty ducts, it's probably not a service call. If you want to start it out that way and have a technician go look at the lay of the land, but if you're thinking, well, I'll send a tech out there and he'll fix it, what's he going to do? You see the nature of this stuff. This is not service call stuff. This is stuff you need to plan for. All right, what do we got here? Hang the units up high. If you look in thermal imaging cameras, you'll notice that the Plywood, when it's down on the deck, is also cold. So you want to get everything up. You want to get as much separation between the cold surfaces as you can. Unconditioned garages do not insulate the ceiling. The code doesn't require it. If you're not going to insulate, if you're not going to air condition the garage, there's no reason to insulate the garage ceiling. If you're going to have the air handler out there, it's much more likely that it's going to sweat if you insulate that ceiling. We would rather that you just let the sun heat that garage ceiling up, because it's not a space that's using energy anyway, and we could use the heat. So when the homeowner asks, like, oh, should I insulate my garage ceiling with the vented attic above it? Well, the ducts might start sweating. It's not going to help you for energy because you're not air conditioning your garage anyway. So the one that you'll have the most trouble with, though, you got to really build some stuff for this one. Unconditioned garage with a cold space above. That's the worst. That's the worst, is a garage where the guy leaves the garage door open and it's got an air-conditioned room above it, so there's no radiant heat. You know, we got nothing. It's sheltered. It's sheltered by a radiant barrier. You know, radiant barrier is sometimes that foil stuff that reflects solar energy. Sometimes what reflects solar energy is just the living space above. So, for example, the worst ones we have to deal with are in high-rise condominiums. You go down to the parking garage underneath this thing, and it's underneath cold concrete because they keep the ballroom like 70 degrees. So the concrete floor is very cold. We go down underneath it in the parking garage, and it's just damp. You touch the concrete. So what do they all want to do? Seal it. Oh, we'll seal it with paint. Well, now it can't absorb into it. It's all on top, so good luck with that. All right, if you're going to conquer this and you're going to be successful, you're going to have to know your enemy. You can't defeat your enemy unless you know your enemy. Do you know your enemy? That guy? Oh, not Mickey. Not Mickey. No, not Mickey. H2O molecule. Absolutely essential for life, but can be a real pain in the butt sometimes, especially when the ducts are wet. So you have to, you've got to understand more about the molecule than is on Mr. Carrier's chart. Mr. Carrier's chart really doesn't teach you anything other than about mixtures of air and moisture. That's all it's about. It has nothing to do with what that molecule is going to do when it actually touches metal or touches foam or touches drywall. There's going to be behavior that can't be explained by the psychometric chart. So we're going to spend a little bit of time looking at that. So that's our enemy. It's a recent mugshot. That is an actual water molecule. He's 2 nanometers. We believe this to be their leader. We call him Mr. Big. And he's little, but they work in gangs. And so they are attracted to each other, which explains a lot of what we're going to go through here. As a matter of fact that they're so much attracted to each other explains this desorption stuff that Mr. Bergman was telling us about. The water wants to bond. It doesn't want to come apart. They like each other. It's very polar. The hydrogen side is negative. The oxygen side is positive. And it's attracted to itself. And if you want to make a list of materials that it does not want to bond with, that would be a shorter list than what it does. So for example, oil, right? Oil, silicas, things that water doesn't bond to. It's a very small list of things that repel water. Because most materials, water gets on it, it's hard to get it apart. You have to do something called drying to get the damn water molecules off because The water molecules want to be on things. Master of disguises. Here found in its liquid form, its solid form, and its vapor form. Does anybody see solid? See the ice? Yeah. Does anybody see vapor? Ha! It's a trick. And you walked right into my trap. You walked right in. All right, this guy just saw clouds. Is that vapor? Huh? Oh, here we go. All right, Sam Myers. I'm showing off your groovy retro tech fogger. Okay, is that vapor? So if the kid gets sent to the principal's office for vaping, the best defense I can think of is, well, that's not vapor. No, sir, I was fogging. I wasn't vaping. I was fogging. These are condensed molecules. You can't see vapor. So, no, that was a trick. Sorry. But I always get somebody. Somebody always like, do you see vapor in the picture? Yeah, the cloud. So that's the vapor. It sneaks in, and you have to understand its behavior to protect against it. Cool it down a little bit. We're going to show you how little raindrops are made. When you think of moisture in the air, we think about the psychometric chart and all that. When you think about the way moisture is going to work on these ducts, remember, most of the moisture in the room is on a surface. So I'm usually in a hotel room when I do this. So I look, well, where's the coldest surface in the room? And it's usually there's an air conditioning grill. Okay, that's, or maybe somebody's got an ice water or something. Well, that's the coldest surface. When you get to the colder surfaces, you will have the higher relative humidities. This is, Mr. Bergman was telling you how to desorb. He was telling you how to get those water molecules off the inside of copper, of the tubing. Now what we're showing you is how does it desorb, or how does it absorb into things like drywall and into things like fiberglass ductwork. Well, what you have to remember is that at 20% relative humidity, that you have a row of 2 or 3 molecules deep. Now, if you're at 20% relative humidity or higher, which is almost anywhere, everything, every surface is covered. There are more molecules on the surface than there are in the air. And you've already seen why. I mean, the air only lets in so many. It likes the surfaces, plus it's lazy. It can give up its heat and stay there. That's all it wants to do, is give up its heat. That's all it wants to do. That's so wrong, you know? Well, only if you're going to get my duct wet. So when you get to 40% relative humidity, you are, in a sense, 3 rows deep in water molecules. And when you start getting to 60, let me see if I can get this to boot. Not Barry. Not Barry. I'm going back. There we go. All right, well, anyway, this is not animating very well. Your computer needs a little RAM there, son. But this would normally jiggle. So if you had more than 8 megabytes of RAM, maybe it would jiggle. But, you know, we're on a budget here, guys. So anyway, this is the molecules flying around in the air, but when you get to 80% relative humidity, most of the molecules are on the surface. And when you think of surfaces, don't think of the molecules on top. This is nothing but surfaces. Why did Dr. Joe tell us that if you want to insulate your way out of it, you need to be R13 non-permeable? Because this happens inside the material. If it's open cell foam, you know how we said that molecules like to be on surfaces? This is nothing but surfaces. It's surfaces through and through. And all these little water molecules want to be all over it. So it starts pretty harmless as adsorption, and it gets carried away as we go. Inside the material, we start with absorption, and then once we get wet enough, we start with absorption, which is where the molecules, there's enough molecules inside this to start pulling other molecules in. Because remember, not only are they attracted to the surface, they're attracted to each other. So once enough of those little rascals sneak in there as vapor, they can start pulling more in. Capillary action, of course. This is from Dr. John Staub, who gave a fantastic presentation at Building Science summer camp a couple of years ago. And I really like this chart. Here's your molecules. So here's 20% relative humidity, and he's got his molecules. He's only one row deep. At 40% relative humidity, he's got a couple of rows of molecules. He gets to 80% humidity. He's got them on both sides of the opening. So when it comes to, well, what kind of materials do you get a lot of capillary action? You know, where the doubling of these would pull others through. Well, this one's a no-brainer, because this was born by God to do exactly that, right? Suck water vertically. And then we started making boats out of it. Did we make it like this way through the boat? No, we went like that. But because we didn't want to pull water through it, right? It pulls water this way, not through. So this explains how absorbed water you do not have to get to 100% relative humidity to become saturated. All you got to do is get to 90% relative humidity, and the material will wet itself after that, because the moisture that's already in there is going to pull the rest right in. So that's why we like non-permeable materials for a lot of different things, because not only does it not have air in it, it doesn't have any of these molecules in it to have this behavior. All right, so you will see many, many times where there's little beads of water all over the tape. But then you touch the duct board, it doesn't have any beads of water on it, but it kind of feels cold, kind of feels damp, but it doesn't have beads of water on it. What's going on? This one is a non-permeable condensing surface. All of the moisture condenses on the top of silver tape. Silver tape does not allow moisture molecules. As a matter of fact, you could probably make a little water bowl that would hold water for a little bit out of tape. It's not a permeable material. So a lot of times people will see this and they'll say, well, it's colder around the joint, or there must be insulation. There must be, no, the only thing going on here is that this is the same temperature as this, but the moisture molecules are going deep into this. They're not on top. And in this case, they're condensing on top. And you'll see that. You'll notice that on non-permeable surfaces, it's all on top. And then when you get to something like this, it'll become damp to the touch, but you don't see it sweating. If a brand name pops into your head while we're trashing air handlers, just keep it to yourself. And then buy me a beer, and we'll trash the hell out of them at the bar. You know, we don't care. So we're not going to do that here, because we do the honorable thing. We talk about you behind your back. You know. So this is a little air handler I invented. It's the Ice Wet 2. And we're going to use it to look at a couple of the things that you have to think about with the air handler cabinets. This is a steel painted cabinet. It's got fiberglass insulation on the inside. It's got a typical draw-through coil, fan assembly with an electric heater. That's a Florida special right there. You can see in those fossil fuels there. Nate's happy, right? You like that? And a matter of fact, you come to Climate Zone 1. We went into defrost in 1996. And it hasn't happened since. We're still waiting for defrost. Well, anyway, the same thing, the Texans were saying the same thing. They were saying, oh, we don't need defrost. We never go into defrost. And then they did. But actually, I'm really not, you might be surprised, I'm not that against a hard freeze all the way down to Miami. It's because of these damn 20-foot snakes, you know. The only thing that's going to keep these 20-foot snakes out of Orlando and Claremont is a good freeze. There ain't nothing out there that's going to eat them or kill them. So the only thing that's going to keep these 20-foot pythons out of here, if you think they're bad, where do you get the iguanas are everywhere? And the tourists like them, just like they feed French fries to the seagulls. You know, they like the iguanas. So when it gets cold out, the iguanas fall like popsicles out of the tree. They do. They just get stiff. So, you know, on a cold day, I can wrestle a boa constrictor, you know, if it's cold enough. How did I get to that? All right. We're looking, okay, we've arrived here. Everything's fine. It looks dry on top, looks dry on the sides. Let's look underneath it. Whoa, it's soaking wet. What is going on? The top sides are dry and only the bottom is wet. What's going on? Insulation's soaked. More than likely, it's a drain leak. What's the number one service call? Clogged drain, right? The bottom of that cabinet, we looked at it. It had insulation in it. What does that insulation become when it gets wet? It's a conductor. You know, not only is it zero, it's not zero. Water is a better conductor than copper. Yeah. So, you know, we like water for exchanging heat, like chilled water, like condenser water. Well, the thing to remember is that your insulation, when it gets wet, you are no longer an insulation. And the same thing's true for the ductboard. Once it gets wet enough, it's going to run away from you, and you're not going to do anything about it until you come up with a strategy to either put it in the dumpster or dry it out. So, you know, while they're standing there crying because everything's wet and everything's going bad, you can just say, well, you know, this is going to dry out in October. I promise. Because it will. So, you know, solution's on its way. Wet on the bottom, you should suspect that the entire, and that's the most common thing we see, is wet on the bottom of the air handler, just the bottom of it sweating. Sometimes you have a cracked drain pan, sometimes you have a clogged drain line, but after you solve whatever got the insulation wet, you're either going to, what we do a lot of times, how many of you like to just tear that out and throw it away? Just tear it out and throw it away once it's been wet like that. And then if you have sweating problems, you're going to like this stuff. If you want to keep stuff dry, don't use that itchy, scratchy stuff. Use this. Foam insulation, great stuff. Things don't want us. Why do you think we put it on cold pipes? Right? It's perfect. So this stuff you can put it inside. And by the way, it's plenum rated. You can't just put anything you want inside a duct. It's got to be 2550 flame smoke rated. This is plenum rated. You can put it inside. And then I'm going to show you what we've had to do for the Ice Queen, the lady who keeps it like 65. And you can't tell her what to do. I mean, she's got a private plane and a helicopter pad behind her house. She's going to get whatever she wants. She's used to that. She's going to get what she wants with or without me, you know. Now, the other thing that happens is you do get this capillary action, obviously, where you'll start pulling water up the sides of it. Even if it began in the bottom, it'll start growing up the sides. Now, remember this, however it got wet, which is usually going to be vapor that condensed. Once it's 48% by volume, 2%. 2%. Once 2% of the air, because that's what insulation is, right, is little compartments of air. Once 2% of that is water, you've just lost half the R value. You just lost half the R value at 2% wetness. If you get to 4% wetness, you're down to 30% of your R value. You're conducting 71%. So this is another reason Joe doesn't want you using open cell stuff. Like if you're going to wrap, he wants you to be non-permeable so that the molecules don't go down in this to the cold surface that's underneath. But that's a big deal. And that's why once you get it wet, you have to undo the wetness before you can move on to the next thing. The other thing to keep in mind is air handlers are built differently. Remember how we had indoor dew point at 55 degrees for an indoor dew point? You have the same dew point right on through here. It drops a little bit at the coil, but you're at the indoor range of dew points. But this is cold air, and so this part of the cabinet wants to sweat. Whereas this A coil has return air up to that point. You should not get any sweat on the back of that. But remember, coils flip. So you flip the coil. Now it's going to be cold all the way to the back just by the configuration. So they don't all sweat the same. One that sweats really differently, no brand names, nobody yell it out. Don't yell it out. Don't do it. The only part of this air, this is what we call a blow-through, right? The air handler's blowing through the coil. The only part of it that could sweat is here. That's it. The rest of it's at the low dew point, but it's not cold enough. It can't sweat. So it's not going to be the same with every single air handler. This is the big one that everybody could do something about tomorrow morning if they just gave a damn. That's the main ingredient. Cabinet infiltration. The first thing we're going to look at is the cabinet infiltration that occurs in this electrical box. There's a knockout. That's where the moisture is entering. The transformer has rust all over it. The variable speed board has watermarks and rust on the variable speed board. How did that moisture get in there? That's at the indoor dew point. Not where the conduit plugs in to the unit. It's dragging the moisture. A Romex connector is not a very good air barrier. You have to add a little something to the Romex connector or it's going to leak. Sometimes it's just a knockout and they don't even use a Romex connector. It's just wide open. But this is the infiltration that causes things to rust. So anytime you're in one of these cold cabinets and you see a lot of rust, look for that path to outside that those molecules are taking. This one also has the breaker, the built-in circuit breaker. It always leaks around those. But here's the big one, just the cabinet leakage. You've all seen that. That's where it leaks. It's just nobody does anything about it until you pressurize it. When you pressurize the cabinet, everybody gets excited and starts sealing it. Oh, there's air coming out. But as long as you can't see it, right, it's sucking air like crazy. You can see it with smoke. You know, give it a little smoke and you'll see this going on. But what's going on here is if you go look do this. When you go back to work next week, go look in the dumpster at all the stuff the guys tore out. Look at the panel covers. They all have the insulation on them. Where is the mold? Where is the mold on the panel cover? Why is it around the doors? Because that's the first condensing surface that molecule got to. We know where it's wet. It's wet all the way around the doors. It's going to be black because things are going to want to live there. And wherever there's an opening, the mold leaves a path for you to show you where the water is coming in. Now, the thing about this kind of cabinet insulation, it is very simple to avoid. You have to use a high-tech product that we recommend. Got to use this stuff. Huh? I don't care. It's okay with me. The painter's tape could be an air barrier. I don't care. I just don't want the leakage through it. Now, the first discussion we had on this was called cold air is not a malfunction. And it was only about air handlers. And my debate was that the tech support people, basically you're building crappy air handlers. And so we're being nice and we're dancing around that. But we both know you're building crappy air conditioners. You know, we know that, but we're kind of like doing the little dance, well, how can we make this better? But the bottom line is the air handler isn't insulated well, it leaks, it's got a lot of problems. So I don't care if you use painter tape, I don't care if you use black tape, gray tape, but this air is upstream of the coil in this case. It's not leaking in and going through the coil. You're mixing this air in raw. So it isn't doing you any favors inside the house either, much less the sweating duct. So is it ugly? I think it is. I think the equipment, if you do a pretty installation, I think the equipment looks better if you don't put the sealant tape on, but it works. Now, if you're inside conditioned space, if it leaks, now my biggest concern is it's not filtered. The air that comes through these cabinet leaks. But it is a lot of air, and remember, we already know what it is. In my climate, for every 110 CFM of cabinet leakage, which it doesn't take long to get to 110, that's 1 gallon an hour. So the math is easy in climate zone 1. It's 120 grains. Okay, so thermal bridging. Why don't we recess the screws so that we can pinch the insulation down? Because if the insulation is 3/4 inch, but then we put a metal drain pan on it and squish it down, that's what most air handlers have. And particularly above this cold metal 16 gauge enclosure. It's a heavy gauge for its UL approval because it's got an electric strip heater. So it's got a heavy gauge metal. And guess what that heavy gauge metal does with heat? It moves it right on through. It doesn't have any thermal storage. It's just going from one place to another. So that's the thermal bridging. So you know before you even go, you know where they're going to sweat. They're going to sweat right there where all that cold metal is squeezing this 3/4 inch insulation down to 1/4. And they've recessed the screws. So everything's pinched together. So you don't have the intended R values. Like if you look in the brochure that comes with the air handler, it'll say, oh, it's got R6 insulation in it. Well, it's mostly R6. What about where you pinched it under the drain pan? What about where you pinched it right here? You know, what about where it's, so we know where it's going to sweat. It's predictable where they're going to sweat just by looking at them. We have some success re-insulating them using technology that we discovered drinking beer. We were drinking beer and it just came to us, what if we put a coolie cup on the air handler? Wouldn't that be cool? And so we did. We took this stuff and you put it, one of my favorite things to do is take this tape, this closed cell foam tape, and put it on the inside of, that's the air handler panel. That's the panel cover that we were talking about gets wet. I like to put the tape on the inside of that and leave the factory scrim, just leave that on there. Put that on there and then do also the cabinet itself. And when you put it together, you've got rubber to rubber instead of metal to metal. The guy gave you, when they built you the air handler, they gave you metal to metal. They didn't give you any gasket. Well, you can add a gasket pretty easily, pretty cheaply. And guess what happens when metal doesn't touch? You've killed thermal bridging. Why do they do it in windows? You know, windows, they do a thermal break. You can do a thermal break. You just have to let the metal not touch the metal. You see how this touching things is such a big deal with this? What touches is such a big deal with this stuff. On the bottom of it, what we like to do is take a piece of white styrofoam and take the white styrofoam, build a little galvanized easy thing, and then put foam over the top of it. And we make it the exact same size as the air handler. This is done, by the way, for the 65-degree customer who's just, you know, this thing's going to sweat. So what we do is we just, okay, the factory is going to be no help. Agreed? If the air handler sweats, how much help is the factory going to be? This is, you know what they do? That's how, the reason I got into cold air is not a malfunction is because they were like, oh, what's your static pressure? Well, it doesn't matter. My air temperature is 50 degrees. Well, what's your static pressure? The air, it's 50 degrees inside the cabinet. It doesn't matter what my static pressure is. Well, yeah, but I'm trying to prove you did something wrong. And I can only do that if you tell me. So anyway, if you get a sweating air handler, none of the factory guys is going to be much help. You're going to have to pretty much work this out on your own. So in our climate, we have to. We have to come up with ways. We can't just drip all over all the ceilings. We have to come up with ways to do this. So sometimes it's not particularly pretty. You can't hardly see this, but this is a air handler on trapeze hangers. That's one of the things you want to do is get it up high. Don't let it be near a cold ceiling. It's got the foam all over it because foam is just not a thing that wants to sweat. It's kind of like the anti-sweat thing. So for thermal bridging, that's what you're looking for. Where are the cold spots? Eventually, somebody is going to tell you the old one didn't sweat. And sometimes it didn't sweat as much. You know why? Because shiny things sweat. Yeah, shiny stuff sweats way more. Where do you see this? When moisture, if you have a slick, shiny wax coating like a beautiful automobile wax job, the molecules make a nice little ball, and they look like this would. And so if we were trying to formulate some sort of a hydrophobic thing, like a sealer or something like that repels water, we would be looking for this. When you've got a more flatter growth of the condensate nuclei, and it's flatter, you do not exchange as much heat, and you don't get as much sweat. How much more? This kind of growth, which is the round one, like would be the nice wax slick surface, is 6 times the amount of condensate and 4 times the amount of heat transfer as if it were more like a film. Flat. A film does not produce as much. This is how we look at it. And a lot is known about this because this has to do in the medical trade with how our medicines are going to work. It has to do, you know, with all kinds of different. There's no molecule that's been studied more than water, because of all the different things it impacts. But this is the difference. This is what you would get on a rough surface, rust. You wouldn't get nearly the condensate that you'll get off a shiny surface. Bypass air. We talked about one kind of bypass air, which is the bypass air from the cabinet leaks. But you also got bypass air around the coil is untreated air that will get the cabinet wet. If you've never seen it, this is a movie of it. And what's happening here, you can see, you can't see vapor, but you can see a cloud, a little bit of a cloud right there. And what this is doing is it's getting this blower all wet. And the guys thought that it was throwing water off the coil, which is often a thing that you look for. So we stuck a GoPro, put a GoPro camera in there, and we recorded it, and we saw the fog. And what it's doing is it's the water source unit is a two-stage coil, but when it's a stacked coil, it's not an interlace coil. So when the second stage goes off, the air comes in raw. And the raw air hits the cold cabinet and just makes a mess. And that's why you want an interlace coil. This is a number one. In my climate, if you have an over-under coil, you can't let that much moisture around. So we basically couldn't do it. If you want to dry it out, you can turn the heat on, you can run the fan, you can bypass it. It will not dry out on its own during cooling season. There's a little trick. Get a dehumidifier. If you don't want to heat up the inside of the house, but you want to dry it out, you could do that. But you've got to get it dry before you can move forward. Here's why I like cold air, and here's why cold air is not a malfunction. If you take air and you chill it down to 50 degrees, and in this case, we have a duct temperature of 72, so it could sweat, but the air will be reheated by the heat load, and it's going to be 40% relative humidity inside the home. Yeah, but the ducts sweat. Okay, well, speed it up. So we speed it up. Now, we got 73 degree. It can still sweat, but the duct temperature went up 1 degree. Maybe it'll help, maybe it won't. We're still right at the dew point. But look what happened. Now we're only at 50% relative humidity. This is why I like cold leaving air. What if we keep going? What? 60 degree leaving air. Not interested. Not interested. That's why I like those 300 CFM per ton. Like I hear all the guys up north talking about like crazy high CFM per ton. In my climate, it's all about the moisture. I don't care how long it runs. Let it run. I want it real slow across that coil because I know that if I get the air leaving at 60 degrees, it's going to be 60% relative humidity. Now that's before we start cooking noodles and taking showers. That's the result of operating the equipment. You're going to add to that with your infiltration, with your showers, with your noodles, with all that. You're going to add to that. So I like to start here. I like 50 degree leaving air. And everybody's welcome to their opinion on that, but my recommendation is that just turning up fan speeds and settling for 60 degree leaving air could maybe get you in trouble. So I say stop, don't do it. Cold air is not a malfunction. And we'll finish it up with the shiny stuff. Let's just explain the emissivity. Do we have infrared users here? You guys know about emissivity. Because you know that when you point the camera at something shiny, you've got to change the emissivity rating. Well, that has to do with how much heat it puts off at the 800 to 900 megahertz infrared range, which is also right where we are with sweating ducts. And so what that means is that if we work the formula that we've been doing here all day, we'll just go ahead and do it. We've got a sloping, shiny surface, a shiny duct, and we're putting all the temperatures in, and we're ending up at 72 degrees as the surface temperature of the duct. Now that's a shiny surface, and it's 73 as the result. Dirty duct. The dirty duct is 75. The temperature of the ductwork went up 3 degrees because it's dirty. So all we got to do is make the ducts dirty. So you can buy the ducts already dirty. You don't have to pay employees to get the ducts dirty, but it is true. So dirty, opaque stuff that's not shiny doesn't sweat nearly as much. And if you notice, 3 degrees is more than you got out of raising your supply air temperature. You only got 1 degree out of that. When you went from R6 insulation to R8, you only got 2 degrees. I got 3 degrees just from getting it dirty. I can do that. And I can buy it already dirty. And guess what? The guys who make this stuff, which is NEMA, once again, remember when we started, we said they can't touch 90% relative humidity. 90% relative humidity is going to sweat no matter what they do. Well, look what happens when it's dirty duct, when it's opaque instead of shiny. Look what happens. You can do 90% relative humidity at low temperatures, but it wasn't even on the chart. And you're golden with R6. R6 is the green one. Look, R6, you're great. And the only difference is it's not shiny. So that the people who do thermal imaging understand emissivity and how that works, but it's how much heat can it give off. So the foil insulation, it's like thermal barrier. When they put the thermal barrier, it's a lot like that. It reflects radiant heat. The opaque white stuff does not. You can buy either insulation. But what I decided to do was make some dirty ducts myself. So I went and bought some black paint, and then I bought some Aquaban. Aquaban is black latex paint with microscopic ceramic beads in it. But basically what it does is it gives me a surface that does not want to sweat. This is Aquaban. See how not only is it black, but it's rough. It's not smooth. It's, you might say, chalky. And that's because they put those ceramic beads in it. Then I tried it with just regular galvanized material, and I also tried it with flex duct. We tried it with metal. We tried it with ductboard. We put some Rust-Oleum on it just for a control, and we had the Aquaban, and then we needed a humid warehouse. No problem. We're in Naples, Florida. It was 2016 when we did this, and it was in August, so no problem. And then we just turned it on and we made it sweat. We basically just circulated the air till we got it to about 30 degrees so that we knew that it was going to sweat. And what did we find? That yes, the Aquaban coating made a big difference. It can still sweat. So you can't say that the Aquaban coating prevented condensation. It made it harder for it to sweat. You had to get it colder. Do you see the difference in how the beads of moisture formed? It didn't want. Now, I've also tried Never Wet. If you've ever used a 2-part Never Wet on grills, it's the same thing. The grill still sweats. It's just so small you can't see it. You've got to get real close to see the little droplet because it's still sweating. It's just small. And that's what we saw here. It could not present condensation, but it was particularly effective on ductboard. Worked really well on the ductboard. Look at the drips. This is totally uninsulated. See how much it's producing? See how we had less here? And then we had the Rust-Oleum had a little more than that. But yes, it does work. So that's wrapped metal pipe. And we could see a difference when we put the coating on it. This is what we really liked, was where we put the coating on the ductboard. It really made a difference because it fogged out cold on the shiny part, and it took longer to get any condensate going on the other one. And then in closing, we'll just mention that when ducts sweat on the inside, we just reverse it. It's the exact opposite. So that happens on infiltration backdraft backwards through ventilation. So the closed dryer is intended to vent out, but the wind's blowing it back through, the backdraft damper's stuck open, you get wet. Same thing with the bath fan. The outside air hits the inside, so the inside gets wet. It works the same way. It's just that the duct is getting wet on the inside. This, we've actually seen dryer vents with puddles of water in them, and nobody has done any laundry. And we go in there and it's like, this dryer keeps getting water in it. Well, you know it's a backdraft. The humid air is going backwards, and it's hitting that cold drum, and it's condensing on the cold drum. And whenever you find a laundry like this, guess what's almost always in that same laundry as this clothes dryer, with the lint on the wrong side of the screen? That's a good indication of a backdraft. When the lint's on the wrong side, that's pretty evident that that's going to be a backdraft. Check your flappers. If you see moisture or evidence of moisture on a bath fan, it shouldn't have come from the room. If you were leaking dry air out, it wouldn't look like that. The reason it looks like that is that's moisture, that's 120 grains coming from outside, and the first condensing surface it hits is the bath fan. Whenever you see a bath fan rust out, why did the bath fan rust out? Because the flapper didn't work. The moist air hit the cold surface and you rusted out your bath fan. Otherwise, a bath fan shouldn't rust out if it's at the same dew point as the ceiling. Thank you for attending this. If you have any questions, I can take them.
On the Aquaban examples of the paint, when you did it on ductwork, and there was one of the slides, the Aquaban was close to the tape, to where you had tape, and you said that you saw an improvement there because of what? I couldn't understand that part. So there was no beads whatsoever on the ductwork, so you were saying?
So you'll notice if you go look at wet duct systems and you're troubleshooting it, that the beads of moisture that people see will be on the taped part because it's not permeable. So the water molecules, they condense on the surface of the tape. Then right next to it, there is no sweat on the ductwork. It's just if you touch it, it's damp. Well, that has the same amount of molecules. It's just this on the top of this one, and it's into this one. So a lot of times when people see tape spots, they think, well, that's where it's sweating. Well, no, it's sweating over the whole thing. That's just where it can't absorb. Any other questions? Yes, sir.
Inside of supply plenums, we'll tear out duct board or duct liner, supply plenums, black mold, condensation obviously going on inside of there. You have high relative humidity upstream of the evaporator coil. Can you speak into that? Maybe migration, anyway, that kind of thing.
All right, the only thing that can make there is one building component that is perfect for condensation. It's called an evaporator coil. There is no other component in the building that is an appropriate place to condense moisture. Maybe on top of the roof, but you know, we don't want to condense into any other building materials, including duct board. But when it comes to how did it get wet in this air handler, it can be the bypass. Because remember we talked about when you leak into the cabinet, that air is not, it doesn't go through the coil, it doesn't get filtered. So if you wanted to reduce that, a simple piece of tape, taping the panel covers, does more good than any high-tech solution you could come up with. You just have, and now the other one is bypass. If you've got a lot of bypass, which seems to happen on package units a lot, where they have too much bypass when you put the cover on. There's also been cases where there's a little metal flange on the edge of the grill, or the edge of the coil, but it doesn't seem to have a functional purpose. It just kind of hides the end bends. Well, that metal may be an air barrier to keep the air from going around. And if you don't have it on there or it rusts away, you're going to have more moisture because more of the molecules went around the coil and didn't condense. But that's the only thing you can do. The assumption that we're making with the wet plenum is that the air hit a surface below the dew point and condensed there. That really shouldn't be, because everything after the coil, we should be gaining heat. All right, I think I'm holding up the next class. I think so.
Thanks for watching our video. If you enjoyed it and got something out of it, if you wouldn't mind hitting the thumbs up button to like the video, subscribe to the channel, and click the notifications bell to be notified when new videos come out. HVAC School is far more than a YouTube channel. You can find out more by going to hvacrschool.com, which is our website and hub for all of our content, including tech tips, videos, podcasts, and so much more. You can also subscribe to the podcast on any podcast app of your choosing. You can also join our Facebook group if you want to weigh in on the conversation yourself. Thanks again for watching.